need it, you can just come find me. Yeah, so this is the Tools and Technology Seminar Series. I think most of you have been here before, but for any new faces, just a venue to discuss tools, technologies, methodologies. Maybe used to researchers, they may be currently in development, they don't always have to be products, so keep that in mind if anyone's ever interested in presenting. It doesn't have to be a finished. So today's speaker is Flynn, and he is assistant professor in learning health sciences. He's actually got a pretty cool background. He's got a background in pharmacy, computer science, and
well, hello everyone, and thank you for having me. Let me do a sound check. Are we okay? Can you hear me in the room, and are we doing okay on the audio? All right, great. So I'm delighted to be with you today and grateful for the invitation. Thanks for having me over to the Tools and Technology Seminar. I have a suspicion that the work that I'm doing is probably not work that is something that you've seen a lot of, but I may be wrong about that. And so my hope for today is that this will be interactive, and as we go through here, that you can help me make this, contextualize this and make this relevant for you, surfacing examples, and I'll have a few stopping points here as we go through. My approach to the title, Untold Assumptions, Technical Idiosyncrasies, and Finite Results. I was asked to give a title a while ago, and I wanted to give a title that would give me some latitude as I put this together, and so I came up with a title like that. It actually worked. I think it's all going to come together quite nicely, but that's where that came from. Really, this is work that I'll be reporting on today and interested in getting your feedback on as well. It's about research and development. We're really thinking about organizing computational or data-driven science to support future evaluation learning and using the outputs of scientific research, particularly when they're fully computable or machine executable, to generate case-specific or patient-specific advice, depending on what's needed there. The intro, which I also appreciate, and just like I appreciate the invitation, this is my background, and mainly it's important to share, I think, our background so you know where my biases are and all the things I don't know about. And so my background is not in computational biology and bioinformatics. I first trained here at Michigan in the 1990s in pharmacy, and at the same time in computer science, although I don't have a degree in computer science. And the professional programmers who I work with, they know what my limitations are, and there are many of them when it comes to programming, which is why I'm fortunate to work with all of them. I'm also, besides being here at the medical school now, after having received a PhD recently, I did a mid-career PhD, received a PhD from the School of Information, getting to be almost 2 years ago now. And so I was offered a position, and I was glad to take it and continue working with Dr. Charles Friedman in the Department of Learning Health Sciences of our medical school. And you may know, or it may be new to you, that the Department of Learning Health Sciences got its name in 2014, had been since 1927, the Department of Medical Education. But as our mission in that department expanded, our mission still includes researchers in medical education, but we also have in our department the Clinical Simulation Center, and the science of clinical simulation gets studied in our department. And then there's a group in our department that looks at organizational learning and systematic learning and infrastructures for learning in the future. And so that's the group that I work with. And so as the mission of the department expanded, the name changed from medical education to learning health sciences. And then I'm also part of a relatively new national, or really getting to be international community called Mobilizing Computable Biomedical Knowledge. And we'll have our third meeting next summer, third annual open meeting at the National Library of Medicine. And so our connection back to the NIH campus at this point through that group runs through the NLM. And we're very happy about that, and we get to work with the folks over there. If you have questions afterwards or would like more information, by all means, please reach out to me. Happy to engage. So the agenda for today, I'll very briefly focus on some issues in epistemology, and very briefly, we need to just anchor ourselves in some concept of knowledge that I hope will be something that we can all live with as we go forward here. Won't take too long with that. Then talk a little bit more about changes in scholarly communication. So the changes that we see in biomedicine are generalized across scholarly communication. So what do I mean by that? I mean the publications, the way the journal world operates is being disrupted by technology in a big way. So how many of you are familiar with preprint servers and use preprint servers or may be interested in them? You've heard of those? So these kind of innovations are coming into the scholarly communication world along with other things, and we're pursuing particular aspects of that, which I'll get to. And then finally, the biggest part here, if these were 3 books on the shelf, I'll spend most time on the design and development of compound digital objects and show you some examples and tell you why we think they're important in our work. So we'll get to that here in a few minutes. So briefly, we have to think about knowledge. If we're going to have knowledge management and knowledge organization, and that's the thing, those are the things that I work on, well, we have to have some definition, some working definition of knowledge, what's being managed and what's being organized. And so you may have heard about or read about or thought about knowledge as justified true belief. That's one way the philosophers think about knowledge. And because of Gettier problems, a refinement was made to that idea, and we come up with justified true belief so long as it's not inferred from any other falsehood. I don't want to go down the rabbit hole of fake news and things like that, but these things are important to keep in mind the way that we think about what is knowledge. So these are a start, but I don't think they're the most helpful for today. So I'm going to show you 3 other conceptualizations of knowledge that I didn't come up with, but that I value because they all point to knowledge as explicit knowledge as something that is information that somehow gets upgraded to knowledge. And that's really the knowledge that I'm trying to manage and organize in the world. And so one way of thinking about that, Luciano Floridi at Oxford over the past 10 or 15 years has published several works in information science and thinks about knowledge as semantic information, which is embedded in a network of questions and answers, which accounts for it. So what I like about this way of thinking about knowledge is it's highly relational. So the knowledge that we have essentially can be thought of either as a set of relations, correlations, causation. You can think of those things as relationships between things. And I think that's helpful to remember that knowledge has some fundamental relational element to it, nature to it. Adrian's thinking from the point of view of computer science and data compression in particular has a little bit of a different thought about what learning is and then the results of learning, which you can think of as knowledge in an information form. So if we have a large data set and we can somehow compress it and get to a description of a model and a description of the data that are less than the data set itself and somehow cohesive and sensible besides, then this is Adrian's concept of 2-part code as knowledge. This isn't code as software code. This is more general than that, but I would point you to a couple of papers in the last 10 years to learn more about this perspective of upgrading information to create knowledge. So I think it's interesting and important. And then Dr. Friedman, over the last several years in our work on learning health systems, has articulated his view of what we're managing and organizing when we say we're in the business of knowledge organization and knowledge management. And his view is that we're organizing the result of analytic and or deliberative processes that are valued by some community. So all of these 3 things under the line there, in my view, are explicit knowledge that somehow can be made explicit. So we do understand also there are tacit conceptualizations of knowledge. There's intuition, there's expert knowledge that lives in perhaps only in human brains, does not make it into a page or a piece of software. But these ones below the line, I think, are the explicit kind that we're thinking we have knowledge to manage, we have knowledge to organize. Okay, so with that lead in, again, this is a reiteration. If you think of an information space, what I'm saying is that for the purposes of this talk and for the work that we're presenting, we think of explicit knowledge as a subset of information, a special kind of information, whether it's Floridi's concept of upgrading semantic information, or whether it's Adrian's concept of 2-part code, or whether it's Dr. Friedman's concept of the results of analytic and deliberative processes. Whatever that is, what we're talking about here is something that is an information-based view of knowledge. An information-based view of knowledge. So there are other views of knowledge, of course, and I'm not trying to be entirely comprehensive, just trying to get to something that's workable. All right, so this is about the end of that little snippet on epistemology. Any questions or concerns about this information-based view of knowledge? Does anything strike you as that we're already off track and we need to find our way back to the path, or does it seem reasonable enough to go forward?
Can you just give an example of some other views of knowledge besides information?
Yeah, so I think one of the major ones is this idea of tacit knowledge that people have they gain from their expertise, and that people have knowledge in their minds that they can then apply when they see a situation, and whatever that pattern matching and understanding that experts have when they engage a situation and quickly understand a problem space and a solution is a kind of knowledge that sometimes never can be written down, never can be truly understood. We can interview people, we can watch them work, but we may never be able to completely capture that kind of expertise. So that's one example. It goes back to that idea of belief, what somebody believes and what those beliefs are predicated on. And we don't always know what people are believing and what those beliefs are predicated on. And so there's something that's a little harder to get at there, for example. Yeah.
About the process of value by community.
Yes.
That seems to refer to the need to find the users or the community who will make use of it.
Yeah.
It involves a kind of classification of varying routes.
Yes. Yeah, and so there's a lot of work has actually been done here on this concept of communities and understanding knowledge within communities. I would just point out that in our scientific communities, when we think about, for example, peer review and the process of peer review, in a sense, when we go through and have a paper peer review, we're engaging some community, right? A community around a journal or a community in a particular scientific space. And it's those individuals and the way they conduct peer review and the feedback that we get, right, that will sometimes determine whether we've reached the bar and we have a new contribution in a space or whether we have not reached the bar and we have yet to achieve a new contribution. So that's one way to think about the community.
Philosophically speaking, when you're saying tacit knowledge, it has those certain assumptions of that person's own personal biases.
Yeah.
But information-based knowledge also has its own biases, and if the information is skewed, then the knowledge is skewed.
Yes. Yes, don't get me wrong. I don't want to give the impression, and we're going to talk more about that somehow information-based knowledge is better or comes without, problems or without biases. It's not necessarily better, but it's what my work is about. That's what we're trying to manage. So I'm just making that distinction.
And as a suggested, based on perspective as well.
Absolutely. Yeah, great points. All right, so this will be important to keep this in mind. We're going to keep coming back to this again and again. So thank you for letting me start with it. And then just unpacking the subtitle here a little bit, there would be lots of ways to think about how knowledge is used in the world. This is just to give some examples, again, not to be comprehensive, but in research and evaluation, we need knowledge to get the new knowledge. We build on existing knowledge in the world. And so we examine what gets published and what our colleagues are doing. We can try to validate it, relate it to other things, incorporate it into other things, summarize it, synthesize it, combine it, extend it, and so on. So when we find a paper or some other scientific output that we value in our own work, we can do all of these things potentially with it. Learning is a different use of knowledge, I would argue, a little bit different. We can study what other people have learned. We can test our understanding of it. We can put our students to the test of their understanding of it. We can teach about it. We can generate new hypotheses also with knowledge. And then my work tends to focus here as a pharmacist. So coming out of the clinical world, the use of knowledge there is oftentimes to get to advice. So we want to understand what's known in the world about a particular problem so we can answer somebody's question. Which medication would be best in a certain situation, for example, or which dose should I use and why should I use it? We want to solve problems with knowledge. We want to make plans that are informed by knowledge. So I put that in this broad category of advice. So however we categorize these things, the point of this slide is just to say that let's not lose sight of the fact that we use knowledge, this information-based kind of knowledge, in lots of different ways. Okay? We certainly depend on it in the research context, but it gets used in other contexts as well. And it's all around us all the time, and this is happening. So, the taking off point for a lot of the work that I'm currently doing with others on a team in the Department of Learning Health Sciences is this idea that explicit knowledge is now being formatted more and more as machine processable stuff. Oftentimes including code, which is ultimately somehow interpreted or compiled to get to machine instruction. And so what I'm encountering in our medical school and around this campus, and I imagine you are as well, are researchers that build their model into a spreadsheet and then maybe send that spreadsheet to other people, or use R or Python or some other technology to create a file, an endpoint, a result, and represent that result, a model. Or maybe use OWL, the web ontology language, or I found, BioPython, other tools. So I don't know, this is TensorFlow from the machine learning world. I don't know the tools that you're all most familiar with, and so they may not be represented here. That's just an oversight. So imagine the tools that you're using to create results that come in the form of something highly structured that's either machine processable or actual code that gets boiled down into machine instructions. That's what I'm referring to. And as more and more of our scientific output comes in these forms, an R package or an R file, an Excel spreadsheet, which, by the way, we find very problematic, and so we're trying to come up with better forms than that, Python code and these other things. This is what we're responding to. This is what we're reacting to. We're thinking about how are we going to organize this explicit knowledge when it comes in these forms. And what's different about knowledge when it comes in these forms than when you have a paper that's intended for people to read? How should we adapt to that across the biomedical enterprise for all of those uses of knowledge? The research uses, the learning and education uses, the advice-giving uses. So I think this is no small change. Are you seeing this change in your own lives and in your own work? Are you feeling this? Does this make sense that knowledge that you're encountering or producing or generating is now coming more and more in forms that are machine processable? This is the trend that you're seeing. Does it make sense? I'm seeing mostly head nodding yes. So we're trying to respond to that. We're trying to think from an information science and information organization and knowledge management perspective how to respond to this change. I think it's a major change. And in particular, our group has been working with the products that come to us after research work has been done in Python or R, or, as I said, I have several projects where the researchers have worked very hard to take something and make it computable in the form of an Excel spreadsheet. And when they write their paper, they put an invitation in to readers of the paper, hey, if you'd like our model, we'll send us an email, we'll send you our spreadsheet. But we find that problematic, and that's not going to be a suitable way to share this knowledge going forward. So we're working on type of problem. So when knowledge comes in these encoded forms, when this
clarify
yeah.
what you mean is not a proper way to...
Not suitable?
Yeah.
Yeah, so the issue that we're going to have is, I have a current project right now in neuro-oncology. Thank you for the question. So if a researcher wants to share some computational model or point scoring system or what have you, and they build the code into Excel, once that Excel file is let out as maybe a supplement, or maybe they email it, or maybe they put it on their web, their lab website, we don't know what's going to happen to it after that. So does somebody then change it and pass it along to somebody else? How do we version that? How do we control the content in that? What we're used to is publishing a paper that goes through peer review and becomes the paper, and if you're going to make changes to it, you have to publish an errata or something that goes along with it. So there's some control in the publishing world over how those changes would come about. But just sending files to each other, we lose a lot of that. And so we can lose track of any changes over time, and we're very concerned about that. We're also concerned that little or no testing might be done on these kinds of things. And so people will quickly transform or move from one use of knowledge to another. So I may send you an Excel spreadsheet with a model in it, and I may have in mind that when I'm doing that, well, we're going to use it for research, and you would never use that to try to answer a clinical question. And then next week, the person that receives that from you, they may actually go back to it and use it in a way that you never had intended. And so who's liable for that? We're concerned about that. Who has the right to use these different things in different ways? So all of this is unclear as we're sending Excel spreadsheets, to each other. To answer your question.
So it's not specifically Excel that you have a problem. It's just the sharing of.
It's not specifically Excel. It's just a good example of where things break down. They break down in other ways, and we're going to try to put some energy into the system to keep those breakdowns to a minimum. Thank you for the question. Yeah, I don't have anything against Excel. Personally, I use it all the time. But for this purpose of scholarly communication, we find Excel and other tools like it could be a Google Sheet equally problematic. And these are some of the answers that I just gave to your question. Well, what are the problems? What are we trying to do? Well, we want to carry along with the knowledge that we share, the scholarly communication that we do. What were our assumptions? What are relevant assumptions? And we also, if we're going to have technical artifacts, we need to indicate to people what are their idiosyncrasies, what's special about that artifact, how should it be used, why was it built the way that it was, and so on. We need instructions on how to use these things safely, but again, particularly if we're going to move them from a research context into an advice-giving context. Software tests are another area that we're looking at. We want to be able to call out identifiable or known biases in these kinds of artifacts so that people that encounter them will also encounter information about the identifiable and known biases. Goes back to your earlier point. Limitations, every paper that we publish pretty much has a limitations section. We're going to have to think about limitations also along these lines. And then past and anticipated impact. So one of the things that we notice with actionable, kind of now executable knowledge, I should call it, the computable stuff, folks want to know, well, who else has used this model and what have they used it for and what is the record of that? So how are we going to help them identify others that have used something and what they've learned from using it? So that's this idea of tracking who's using what and understanding past and anticipated impacts. And this is quite different in the library world, because in the library world, library ethics oftentimes would direct us not to collect information about who's reading what. And so we have a tension there. If you haven't seen it, I don't know, has anybody seen this or read this paper about a year and a half ago? I think it was in the Atlantic. The scientific paper is obsolete. I'm sorry if that's a bummer. But here they have it, burning up in front of our eyes. And this article is, I think, worthy and builds on what I'm saying here. So if you haven't seen it, I recommend this to you. It points out, why we're now getting to this point where what we're doing with scientific articles is not going to suffice in terms of our overall scholarly communication. And so they talk about a lot of these same issues. As the artifacts that are coming from research change, we have to change our approach to communication, the argument. So we're working on and trying to figure out a lot of things about how to communicate this kind of knowledge when it comes in this encoded format. How do you document that, version it? How do we verify from a technical perspective the code that's there, test it, and provide tests for it? How do we document and share the performance of the code? How do we validate it in future scientific work? What about error handling? So if you build a model that has a set of inputs and outputs, and you can precisely tell someone this is exactly what you need for your inputs, and then this is the type of output to expect, well, what if you don't get exactly what's needed? A lot of work in the software world goes into handling the edge cases and the error handling. But sometimes when we're building models in the research world, we assume sort of the perfect state, which is that we're going to get exactly the inputs that we expect and nothing else. So there's oftentimes work to do if we're going to use these things in other contexts to make them more robust in terms of their code and add more code to them. We have to think about how we would support some of these models as they become products for the long term, integrate them with other systems and platforms, license them, handle liability issues, point people to dependencies or otherwise help people overcome problems with dependencies or underlying code that we need in order to run some model that we have. Yes?
Somewhat tangentially, but the error handling portion reminds me of a quote from a guy named Rick Cook,
Okay.
who says that the universe and programmers are currently at odds with each other, where programmers are making bigger, better, idiot-proof programs, and the universe is making as it stands, the universe is winning.
Yeah, right. So your point is well taken. So the work of knowledge management and knowledge organization is to counter chaos. And we're only going to be able to counter it up to some degree, right? Which I think that's how I'm interpreting your point. Is that we're only going to get so far. So long as we're not hurting people and we can maintain momentum in science, then I think those would be good, reasonably good goals. We won't get to perfection. So these are the things that are on our mind that we're working on. Let me just be clear about something. When a journal says you're done when you have a link in GitHub and you put your code there, we're saying no, that's not sufficient. Okay? So that may be the first step. Okay, but we're saying that's just not going to work. And I don't know about you, but I've met many GitHub repositories now full of interesting stuff where I just don't even know how to get started. Because, the README is essentially blank or has a title in it, and that's all. And of course, in context, if you're working with the group that created that stuff, you probably don't need that information, and you could probably understand what's there. But the whole idea of scholarly communication is to transfer what we know from one place to another place, or from one person to another person. And to transfer it, you have to do a lot more documentation. And we don't often see that. And it's hard, and it takes a lot of work. And so it's going to change the way all of us work, and it's sometimes not the most fun work to do, but this is what we're going to have to adapt to. So, if the scientific paper truly is obsolete, the core that I want to spend about the next 15 minutes on and then have time for Q&A, the core message here is, so, okay, well, if not the scientific paper, then what? What are we going to do? What are people thinking about what comes next? And these little images here are some examples of things that I'll get to in a minute. So what's next after the scientific paper? And for this, because I'm a pharmacist and I think all of you will be very familiar with the periodic table. For this, I'm trying to anchor in something and have common ground with everybody in the room. And so, does anybody, by the way, recognize this compound? What's that? I'm looking at some in the back of the room right now. It is caffeine. All right, so this is caffeine, so we've got some hydrogen and some carbon and some nitrogen and some oxygen. And we're all used to, I know this is a very simple small molecule. As a pharmacist, those are the ones that I know better than some of these more modern drugs. But we're used to this. Okay? We're used to this idea that you can have molecular structures and that there's some fundamental underlying set of elements that ultimately get combined to form these structures. So I want to use this as a simile. So chemical compounds are like, and this is where I'm coming to this idea of compound digital objects. So now, in the library and information science world, and in the research world, where it overlaps with the library and information science world, say, for example, at the National Library of Medicine, there are discussions going on about these things, compound digital objects. Sometimes they're just called digital objects. And the idea here is to begin to take several parts and pieces and put them together and basically create something that's akin to a molecular structure for information artifact. Now, we don't have a periodic table for this, but we can begin to understand that there will be different types of information artifacts that ultimately come into these objects. We may have binary artifacts. We may have code that's, in this case, human-readable programming code, linked data, tag data, tables, narratives, slides, images, waveforms, audio, video, and other things besides. This is not a complete table. Does the point make sense? Parts and pieces being organized and reorganized to generate structured objects. That's really the main point. So I'm fortunate to have the cross-train in pharmacy and information science because, I can sort of begin to see what's happening in the information world in a similar way. When I had my organic chemistry and all those courses long ago, we were working with those kind of molecules. And we can give these objects structure. We can set a standard way to build an object and what needs to be included and what are the parts and pieces. And so that's the work that our group has been doing. We've been pioneering some different types of objects, and we have properties in mind that we want to achieve, just like you sometimes do when you think about synthesizing molecules. You think about their properties. So we're thinking about the properties of these objects and what we're trying to achieve with them to upgrade and improve scholarly communication as a response to having more and more different artifacts to manage in the world. One thing that we can do, not unlike chemical bonds, we can declare different types of relationships in these objects between these artifacts. So we can have artifacts that can be converted back and forth one to the other. We can have artifacts that define other things. We can have artifacts that provide values, like a value set, to other things, and then compute using that value set. We can have descriptive artifacts. So we can actually, using the semantic web kind of technologies that I'm sure you've heard of, we can declare these kinds of relationships, and we can build objects where these relationships are made explicit. This is what we work on, and we work on this because we want to make these digital objects findable, somehow verifiable. So we want to have kind of a checksum mechanism that you can tell once an object is out there that the object hasn't been tampered with or otherwise changed. Corroborable, we want to include somewhere in here provenance and other critical information of who created the object, when, for what purpose, and why and how. Our group in particular, because we're talking about executable code, we're very interested in activating objects. We're very interested in running the code that we embed in these objects. And so we think about that, and then we're interested in interoperability. We want to create objects that don't just work in one platform, but work across many platforms. So this is the tall order. The science, the R&D that we work on is, well, how do you build objects like this, other properties, and what can we achieve with this method? So all of these things I just mentioned, you can kind of map them back to these various types of higher level artifacts. We can have API service descriptions with our objects, checksums. We can have versions, persistent unique identifiers. We can embed, and we are embedding software tests in our objects. So not only do you get a snippet of code, but you get some tests that you can run to ensure the code is operating as the creator intended. We can do bundles and put binaries in there and try to handle some dependency problems that way, overcome dependencies that way. We can include samples of data. We can have statements about purpose bias, limitation validation. We can provide good instructions and licenses, and other things besides. Yeah, Jeff?
So what is the way that you're trying to bundle all these things together? Because, first, this looks like a data dryad nightmare of trying to get all the little pieces together and figure out.
Yes, that's right. So not unlike being presented with, a whole lot of elements, in different bottles and bins, and trying to synthesize all of that. So the good news in the information world is if we declare a schema and a standard for one type of object, and I'll show several examples, then we can actually write software that will facilitate, and in some cases automatically build these objects for us. But the automatically build part is tricky because, as I said, some of this is going to require all of us to include additional information that we may not be including today in our scholarly communication. And not all of that will be obvious and automated. So when I get to the examples, I think it'll better answer your question. Okay, so we're building this on 30 years of thinking about digital objects. And a key paper in this space was published in 2006, but actually refers to information from the mid-90s. And it's this paper by Kahn and Walensky, a framework for distributed digital object services. Okay, so this is an anchoring paper in this field. When we go back to it, more current thinking based on Kahn and Walensky's work and with their help is this idea of rethinking the internet and its purpose. And so the rethinking goes from this idea that we've really got embedded in our minds a lot about email and the World Wide Web as having hosts and ways to reach hosts, to get web pages and email and things like that, to thinking about the internet as organized around the discovery and delivery of information in this object form. Okay? So when we think about this problem of scholarly communication and we think about modern internet technologies, the idea is scale. The idea is to scale this up in a big way. And so others are working on this kind of digital object architecture idea. I imagine we're headed for a world where we'll have a whole variety of different, highly specified and well understood types of these objects, but that's what we're working on today. All right, so let me give you some examples. So from the Research Data Alliance, from the RDA, within, I guess this is just about a year ago, they published their current view of digital objects for essentially data sets and wrapping data sets with additional metadata, which would allow those data sets to be used by other people. That's the goal. And their idea of a digital object here is a very general idea. And so they say, well, you're going to have some bit sequence or content in your object. You'll have some metadata describing that bit sequence and other things about it. You'll have some other data or information about its operations, and you'll have a persistent identifier. The persistent identifier shows up in all of this work. So the idea is to have large ecosystems of these objects, the same way that every PubMed article has a persistent unique identifier, the same way that what gets published in journals has a persistent unique identifier, the same way that books do, these objects will have them as well. That's sort of one of the fundamental pieces of metadata. So you see that in all of this literature. So their idea, they're thinking a lot about data objects, primarily data sets. Out at Manchester in the UK, Carol Goebel, who's a computer scientist there, has a group, and now for getting to be 14 or 15 years, they've been pursuing something they call the research object. And they build these objects and they have platforms for them. They have a specification of what goes in a research object, and it includes these kinds of things. A publication, one or more publications, a data set, one or more of those, some results that are somehow described, workflows, how did you go from the data to the result, slides that maybe describe the work, some additional metadata describing the whole scientific process, and some logs that come automatically from machines that were used in the process, and bundling all that up and putting it in a package. And here, this little box is the box that indicates the type of objects that they're creating. So we talked to Dr. Goebel periodically since we're working in a similar space, and we have some ideas of how our teams can work together. You can go online and you can find the standard that describes what is a research object. And they have built tools that will look at a digital object and basically can indicate whether that meets their standard or not. So they built validation tools for research objects. These objects are highly heterogeneous. They can have lots of different things in them, which I think makes them interesting. The objects that we're pursuing are a little bit less so. Yeah, so notice the parts and pieces here, and then they give sort of this idea of an example. And again, they're representing over here, they have a formal model of the relationships between some of these things. So it's not just having 6 or 10 files in a folder. It's actually having files that can be zipped up in a folder along with a description of what those files are and how they interrelate. And that description is often going to be an RDF and machine consumable. So that description itself becomes metadata that can be fed out into other library systems to support search and finding things and so on. So that's important. It's important to recognize those relationships between the objects, essentially between the atoms there of the object. So in their case, they're really responding to what I'm sure you've all heard about and talked about before. They're really responding to this problem or challenges we're having with scientific work in repeatability, replicability, and reproducibility. So their main motivation for creating research objects and platforms that can communicate and manage them is so that research processes can be upgraded and improved and our scholarly communication is better so other people can verify our work, so that we can verify it, other people can, and extend it. And so they've built these highly heterogeneous objects. Their scope is mostly covering information about research studies, and they're really not focused very much on the executability. You can put code in one of these objects, but their main focus is more about making sure the code moves from place to place as part of the communication, not so much making it go, making it run. And what we're working on is a little different, which is why I point that out. So these are some things that if you look at that RO spec, you'll read about. Again, just a reminder, what space are we in here? Our group here at Michigan, we're responding to these new types of artifacts, particularly when they're machine executable, being the results of research work. And so we have also specified an object that we call a knowledge object. And this knowledge object also has a set of parts and pieces that are interrelated, and we have a formal model for these objects. And so we'll have some metadata with a persistent unique identifier and a knowledge object ecosystem. We will have some implemented algorithms, some code, maybe some tests. And then we'll include also So the identifier, the code, some tests, an API specification. So every knowledge object that we create carries its own API specification. Because we're very interested in making it as easy as possible to get this code running and interacting with it. So every object becomes a microservice API, essentially. And we include some technical details also in the deployment specification. So we put these files together, again, following a structured format like a standard, and we create what we call a knowledge object. This is part of a larger project, and I'll show the software here as I end up with a brief demo. Happy to talk about it more. All of the work that we've done is represented at kgrid.org, and we call our project a knowledge grid. The idea is ultimately to take advantage of the internet and have these kinds of objects moving in a fluid way throughout the research world and beyond. So we're building objects like this. We have many examples now. And we're starting up new projects where we're taking these kind of objects into a project, working with folks who do predictive modeling, who do other kinds of work where they create or generate this kind of machine executable knowledge artifact. And then we're working to help them manage that over time, version it, keep it up to date, and so on. So a key thing, our key commitment in the knowledge grid, which makes these knowledge objects somewhat different from the other compound digital objects that we're seeing come into the world, we think about this process of activation. Our commitment is to look at the static objects as resources. At the same time, every object in this ecosystem that we think of as the knowledge grid today, because it has this API specification, should be activatable. We should be able to activate it and get a service. So every object can be thought of as a static resource, also as an enabler of a web service. And that's the exploration that we're doing. That's the R&D that we're doing. How do you build objects like that? How do you make them work at scale, and so on? We think this is a general need in order to get to these kind of micro-knowledge services. And so that's why we're on this path. In the Department of Learning Health Sciences, we think of large-scale learning systems. And so we think of this technology, the knowledge grid, as support for those kind of large-scale learning systems, which are coming about in the world. So we hope that our timing is good. Again, knowledge objects are a little different than research objects or the more general digital objects used to carry a data set, perhaps. We're interested in externalizing and modularizing the kinds of knowledge that ultimately can be used to generate advice in EHRs or used in a classroom for education purposes or used to propel research and evaluation. So externalize, modularize, get a service or an API. These are the things that we're going for. And so in order to do that, actually I should say moderate degree of heterogeneity. We don't have as many different types of things in our objects as they do in a research object. Our scope is not so much an entire research study as it is some body or collection or module of computable knowledge. And we're very much interested in making these things executable very quickly and as easily as possible without the person who encounters them having to do a lot of technical work. So those are our goals. So you may get from these ideas that our two projects, the research object project and the knowledge object project, could fit together, and it's true. When we talk to the people at Manchester, they think about results one way, we think about the results in an executable way. You can imagine a future where a research object is carrying one or more knowledge objects, for example. So these things can work together. We're not in direct competition in that sense. So some of our projects that we currently have going on are packaging predictive models for chronic kidney disease. That's a project in the Joint Institute here in the medical school. And so the models will actually be created in China on a large data set there. And then the idea is to ultimately deploy them to generate advice in patient care. We provide APIs for a drug ranking algorithm in neuro-oncology. So this is a set of researchers here who have created an Excel spreadsheet. They now want to share that with 8 other sites around the country. They need a different way to do it that they can control, version, test, and so on. And so we're helping them upgrade what they've got with the knowledge object method. Providing APIs to do EHR integration for a risk scoring tool in OBGYN hysterectomy in particular, and then combining preventative service computable guidelines, so taking recommendations, making them computable with utility models of the value that you get from doing these preventative services as an individual and giving individualized guidance on these recommendations. These are the kind of projects that we currently have. Let me finish with a brief demo. So in the space of clinical pharmacogenomics and genetics, there's a group at Memphis and Stanford, federally funded, called CPIC. Has anybody heard or worked with CPIC at all? Okay, it's in the pharmacy and pharmacogenetics area. So Russ Altman at Stanford, you may have heard of, is part of this group. And what they do is they create guidelines. And so they're helping us understand how do we go from genotype to phenotype for certain genes and enzymes. And then once we know phenotypes, how do we go from phenotype to recommendation drugs? So they take the basic science, they bring people together in groups, and they create these guidelines that are really intended to take this science and apply it in practice, apply it in care, provide patient-level advice. And so now, let me go out of PowerPoint, show you, and I'll try to do that up here in the middle screen. And now I'm going to go over to Chrome. Okay, here we go. All right, so CPIC is the website where this material comes from. So we're working with this group. They're in Memphis. As I said, they create guidelines. So this is their website today. You can go here, see all the guidelines they have, different drugs and genes. We'll look at one today. We'll look at one for SLCO1B1 and the drug Simvastatin. So here's what they create. So they create a PDF, obviously human readable, explicit knowledge, meant for publication, does get published in a journal. Those tables that I just showed you on the slide, this is where they came from. So their hope is that folks around the country and around the world who are in clinics and hospitals will find these PDFs, will go back to their home institutions, and will somehow take the knowledge that's here and encode it into their electronic health record systems in order to improve drug selection and drug dosing. And they're hoping that that pretty much happens at every place where an EHR is being run. And of course, that's a big challenge and will take a very long time. So if we rely on that way of sharing this information, which is our current practice, okay, it's going to take a long time to adapt to this science. Right. So how can we do better? So that's the kind of thing we work on. So we've taken pretty much every guideline on their website and every mapping table they have from genotype information to phenotype information, and we made it computable. Okay, so we've taken it out of the PDF and we've turned it into pretty straightforward software. And so what you're seeing here is the end result of our having done that. So imagine you have a patient and now you get some lab values back, and now for all of the drugs that are on that CPIC website, we're no longer relying on the tables in the PDF. We've just made the lookup automatic. Very simple, straightforward, not difficult to think about how you would encode that and do that. This is pretty simple mapping and if-then kinds of statements. But we're trying to make this information much more actionable and apply this knowledge to patient-specific cases in ways that you really can't do with a PDF. That's this idea of mobilizing the knowledge.
The patient data coming from them?
So this data would come from the lab.
Are they input that, or would they
How
be
do
able
you
to
do that?
manually input that, or would they be able to
Yeah, so
integrate it into their?
yeah, so good question. So in what's happening today in some advanced sites is these data are coming in a coded form that is reliable from the lab, and they can automatically be processed by computer to get to the recommendation or to get to a report. But in many places, that's not the case. In many places, these data are coming back from the lab in a paragraph, right, where the lab sends back a result, but it's not directly computer processable without a lot of help. And so in that case, that's a barrier that we have to overcome. So folks in pathology, folks in pharmacy, folks doing the basic science here are all getting invested in how can we take some of the friction out of this system and make this actually happen the way you described. But in most places today, it is not happening the way you described. I wish it were happening the way you described here at Michigan Medicine, not yet, but people are working on it. So this is just a prototype that shows, well, once you have this computable knowledge, here's what we can do with it. But this app, all of the knowledge in this app, all of this explicit knowledge, is actually kept in these objects. And it's all API driven. So any app can tap into this. That's the point, not just one app. So the app itself does not contain or encapsulate the knowledge here. It's all an API story. So what about those APIs? So this is prototype software that we've created in our essentially eLab for this work in the knowledge grid. So this is a library concept for knowledge objects. So you're looking at essentially a digital library concept of the future. Each one of these items is an object. And to save time, I just queued up the object that I'll walk through today briefly. So searching for Simvastatin, I find this object in the library, and I can open it up. And the first thing you encounter in this prototype is something that looks a little bit like a card catalog card for a book. Just some very basic metadata here. Also a link back to the original page where that recommendation came from. So we want to, as best as we can, take advantage of what the net allows in connecting. But also in here, and that earlier abstraction of what a knowledge object is now represented here in real form. We have a variety of parts and pieces. One thing that we have is some actual human-readable JavaScript code representing a part of these guidelines. But then we also have, not that one, oops, the other one, an API specification. So I mentioned every object that we create, we want to make it also enable a service. And so you have to have the code and the API specification in the object. And that's how we build our object. Once I do that, and I have all that information organized in a particular way, this goes to your earlier question about how will we do this at scale and how much work will this be. And so what we're basically saying is if systems could begin to produce objects that fit this standard, then we can potentially gain some efficiencies. And so one of the things we can potentially gain is being able to pretty quickly run these items here. See, this is what happens when I... I think I want figureactivated.org. Let's try it. What happens with live demos? So what I'm trying to do, and I won't waste too much time on it, I'm trying to push this item over to, out of the library, over to, yeah, I think I have one little issue that's not working there. So I'm not going to, given the time, I'll stop here. But the idea is to show you the API that goes along with that object. So what happened is, as I was setting up 2 or 3 times on another computer, I didn't quite get that right. But in any case, not to troubleshoot in a moment. What happens, we basically show that you can take what's in the object, get to the API, and now you have something that can be integrated with others. So that's what I wanted to show you today. Thank you for your time and attention. I appreciate it. Questions? Yeah.
So in this last example,
yes.
The application describes the calculator as input very efficient. Work created a oil sensor of that.
Yeah.
You have all the logic and algorithm encoded under the hood. Mm-hmm. You also make, I imagine you will also make this a sizable algorithm, future runs of.
Yeah, so if we're talking about rules and rule sets, they get managed in one way in the world. If we're talking about other types of computable artifacts, so predictive models, for example, need to be calibrated and recalibrated over time. And you may be referring to something like that. In our work with the folks in pediatric neuro-oncology, they have a scoring model. New drugs are coming all the time. They anticipate having to update their model 3 or 4 times a year. And so one of the benefits that we want to show with our work is that we can create tools and tooling that will allow people to more easily manage the update process and push out new updates to those people who are consuming these objects.
And then the consumer of such information, they have different attitudes. Some are prone to worry, others just ignore it. You also study consumer behavior.
Yeah.
Receiving such.
Absolutely. There's a lot that we have to learn there. So in the clinical world, there will be many concerns, and there'll be a very high bar before people let me push new code into their system, and that's a good thing. We're going to have to come up with ways that people can trust what's being produced, understand its source, where it's coming from, perhaps subscribe. We're thinking about publication and subscription services that would let people subscribe to one or more objects or a collection. And then when anything is changing in that collection, be notified of those changes and then ultimately decide for themselves how they want to handle those changes.
My question was actually very close to that. Like, I was curious, you said you need enough people in this to make it more efficient. How are you going to get that buy-in?
Yeah, good question. So, so the good news is that we've already got a start on that. So this group that's been meeting at the National Library of Medicine will be the third summer this year. It's about 150 people, and major stakeholder groups are represented there. So we have folks who do data science work. We have folks who are in the library there. We have folks who are thinking about the ethical and legal and social implications of these kinds of artifacts and changes as they go through the world. And so that particular group, also we have people from industry, as you would expect, and otherwise. So the work that's going on there is to set standards and begin to make this, this kind of thing more widely available, build that kind of buy-in that we'll ultimately have to have, if we're going to be successful. My sense is that our knowledge object may not be a winner. It's R&D. We hope that it's useful, but that these objects, one way or another, people will be creating these kind of ecosystems for these kind of objects. I think that path seems pretty clear, but who can build the best object? That's what we're trying to do. That's part of the work. Yeah. Yeah, I think you were first.
So in your compound digital objects is to organize the files, organize the data better. I understand that by the formats, but I think another way that we usually use is to organize those things by a smaller question, smaller topic, and then put the thing related to that question together.
Mm-hmm.
Like in chemical molecules, we sometimes care more about not only each of the elements, but also care about the functional groups.
Mm-hmm.
So I think,
yes.
How do you think about organize them by topics or smaller?
Yeah, so actually I think there will be many dimensions that we would need to think about for organizing. Topics would be one, maybe not the only one. Types might be, different types of objects might be another one. So we think about, oftentimes we go back to metaphors and examples from the library world that already exist today. So if you think about special collections in a library where people curate and manage and bring things together for a particular purpose, that may be somewhat akin to what you're talking about. It may also be the case that we find that several different types of objects always, need to be used together, more like a functional group. So independently, they're not as useful as they would be if you had three things working together, for example. So those are lessons that we are learning along the way, trying to figure that out. Currently, when I came over here today, the work that we're doing this morning, like right now, is to think about collections of objects and how would you describe a collection and how would you describe the logic that drives that collection or cause that collection to come to be. Yeah.
So you said the GitHub is not sufficient, and I think the communities recognize that, and they created things called Docker that kind of encompass the code and the environments and programs necessary.
Yeah.
Usually by BioPython. Where does that fall short?
Yeah, so containerization strategies like Docker are also very important. And we've done some work with containerization as well. We still, in containerization, may not be sufficiently attending to the library use cases that we have and the curation cases. So having a container is great. Having a container that is part of a larger object that has the material with it and a persistent unique identifier and somehow gets peer-reviewed and published in a future state is a different thing. So it's another one of those. I think that's the containerization story is important and may help us overcome many dependencies. If we can give people, the necessary software to run different types of objects. In September, we worked with a group at the University of Indiana Medical School on some machine learning models that they had, and we used a containerization strategy for that. Another concern that we have with the containerization strategy is a security concern. And so when you adopt all of these different technologies into your technology stack or otherwise into your objects, you're also adopting, any security gaps and other things that are there. So Docker today, over on the other side of this campus in the hospital, I don't think it's used very much because they're concerned about the security of it, for example.
Last questions? All right, let's thank our speaker one last time.
Jackie.
Yeah.
Does our group participating in China? I know.